Good morning, my dear students. Okay, coming to the another type of problem, that is a distance problem by using elimination method. Okay, so here in the almost all, in the module 2, in the all the videos I use the images from the SBRLS textbook. Okay, so I wrote here the referred by SBRLS textbook. Okay, so here some another type of problem you are going to solve in this video. Okay, so that is the some distance gap. This is most important problem. So many times in examination they may ask. Okay, so this type of problem. Okay, so that is the type 4 problems on distance gap. Distance gap nothing but this is how element will be there. So some they will fix this element some distance. Okay, that is some 0.12 0.15 mm. Okay, like that. Okay, so here problem I will read the question they given like this. Okay, a bar is having a uniform cross sectional area, that is a uniform cross sectional area for the given bar is 300 mm square and is subjected to a load of P is equal to 6 kilonewton. Again here the unit is also wrong, so K should be smaller letter, N should be a capital letter. Okay, so P is equal to 600 kilonewton as shown in the below figure. Okay, determine the displacement, field stress and up reaction in the bar. Consider it as a 2D bar element. So here they are only telling there consider two element means you have to divide this element. Okay, and use the elimination method of handling boundary condition. Okay, to solve the displacement risk, all those things. Okay, and take Young modulus is equal to 200 gigapascal. Okay, this 200 gigapascal is standard for all the bars. Okay, so look at that, observe the diagram here. They given one bar element, that is here they are, this bar element is fixed some at a distance of 0.12. Okay, so this end is fixed, this end is fixed. Okay, exactly at the middle they are applying the axial force is equal to how much, 600 kilonewton. I am telling you this kilonewton, capital N is big, capital N, K is the small letter. Okay, so P is equal to 600 kilonewton. Area for the element is equal to 300 mm square. The given length of first element is equal to 150 and second element is equal to 150. The distance between the gap that is fixed from this element is given is 0.12. Okay, calculate what is the displacement. Okay, so using elimination method. Okay, first note on the given data here. Okay, so Young modulus is equal to E is equal to 200 gigapascal, convert into Newton per mm square or megapascal, both are same, that is 2 into 10 to the power of 5. Okay, and area of an element is equal to 300 mm square, the given area. Okay, since it is a two element is there, so both the elements are same area only, they are not given separate. So consider A1 A2 is equal to 300 mm square and load P is equal to at exactly middle at node number 2 is equal to 600 kilonewton, that is a P is equal to 600 kilonewton, and length of element 1 is equal to 150 and length of element 2 is equal to 150. Suppose if they given that 300 means you have to divide this and consider half of that. Okay, so length of element 1 is equal to given 150 and length of element 2 is equal to 150 and force 1 F1 is which is fixed, so consider 0, and force 2 at middle is equal to 600 kilonewton is given, so I have to convert into Newton, 600 into 10 to the power of 5 or 6 into 10 to the power of 5 Newton. Okay, F3 again here F3 also here the fix is there, consider 0. Okay, so once if you note down all the given data, go for apply the procedure. Okay, what is the step number 1? You have to convert the you have to compare the given problem into and you have to draw the FEM model. Okay, first number 1 FEM model. Okay, modeling the given bar considering the two bar elements. Okay, so consider from this to this element is one element, that is node number 1 to 2 and 2 to 3, L1 L2. So the given L1 and L2 at node number 1 F1 force is acting and F2 force is acting, F3 force is acting. Okay, Q1 nothing but the displacement at node number 1, Q2 be the displacement at node number 2 and Q3 be the displacement at node number 3. So L1 L2, this is element number 1 and this is element number 2. So the first step is got over finite element model. Okay, so coming to the second method is what you have to calculate the element stiffness matrix for each element. Okay, same, the stiffness matrix for the bar element is given by, this is a standard formula, already we derived this. Okay, by using minimum potential energy and direct method, that is Ke is equal to Ae by L, 1 minus 1 minus 1 1. E stands for number of element. Okay, so since it is only two elements are there in this problem, so for element 1 K1 is equal to area we know, Young modulus we know, length is you know. Okay, substitute, you are going to get 4 into 10 to the power of 5. So if you 4 multiply, that means 4 minus 4 minus 4 4 Q1 Q2 and 1 2, that is this is called as node number. Since it is consider only one element, node number 1 2 are present, so take 1 2 1 2. Okay, for element 2 also same, Ae by 2, that is A2 L2 by Ae, that is what A2 E2 by L2. So if you substitute all the values, you are going to get 10 to the power of 5 4 minus 4 minus 4 4. Okay, so you have to simplify this, the both the element the outside to the power of is same. Okay, don't here make it 10 to the power of 6 and don't calculate like that. Okay, why means you are while calculating the global stiffness matrix, which is helpful to take the common both. Okay, so this outside should be same, 10 to the power of 5 10 to the power of 5 only. Okay, so don't make that here 10 to the power of 6 3. Okay, so you have to calculate, you have to simplify such a way that both should be same. Okay, so this is about the element stiffness matrix for first element and second element. Okay, so global stiffness matrix is equal to what? K plus K1. So combination of all those, since it is a 3 noded element is there, 3 into 3 matrix, that is 4 minus 4 0 minus 4 8 minus 4 0 minus 4 4. Okay, I will repeat how to take these values. Okay, so here how many elements are there here? 3 elements, that is a 3 node 3. Look at this 4, how we got means this is it is situated at a node. What is the node number position for this? 1 and 1. So look at 1 1, you check and the both the matrix. Okay, so 1 1, 4 is there, here not there, 4 here not there, 1 and 1, so 4 plus 0 4, like that. Okay, here minus 4 is situated 2 and 1, so 2 and 1 you add here both the matrix, 2 1 1, this is minus 4, here not there, so minus 4 plus 0 minus 4. Okay, and 0 0 is situated what? 3 and 1, 3 and 1, here also not there, here also not there, so 0 plus 0 is equal to 0. Like that you have to calculate the global stiffness matrix for this, that remaining. So how you got minus 4 here? 1, it is minus 4 is situated is equal to 1 and 2, so 1 9 2, check here, so 1 9 2 it is there, here not there, so minus 4 plus 0 is equal to minus 4. Okay, so q2 2 8 is there here, 2 2, so it is situated in the node place of 2 into 2, check here, 2 into 2, so this is 2 2 4 2 2, 4 plus 4 is equal to what? 8. Okay, like that you have to calculate the global stiffness matrix. Okay, and the nodal displacement vector is equal to, since it is 3 elements are there, so q1 q2 q3, that is u1 u2 u3, both are same only. Okay, so now global load vector, this is most important here. Okay, global load vector force. Okay, so we can see that the gap between the node 3, so it is gap between the node 3, not node 2 or node 1. Okay, gap between the node 3 and support at the rigid end. Okay, and there is a gap is there and support at the rigid end. Therefore the force at node 3 cannot be equal to 0. So force 3 cannot be equal to 0 because here some distance is there. Okay, thus the load vector can be written as, so like that. So how many forces will be there? F1 F2 F3 minus K13 K23 and K33. Okay, so look at this is a 3 into 3 matrix. You just draw K11 K12 K13 and K21 2 2 2 3 and 3 1 3 2 3 3. The last third element, that is K1 K2 K3. Okay, where is that code? Okay, this one, and which is multiplied with this distance. Okay, that is A3 A3 A3. Okay, so where A3 is equal to what? The given displacement is equal to 0.12 mm. I hope you understand this. So since this belongs to 3 into 3 matrix, suppose that is, if you write a matrix that is the third element rows, that is 13 23 33. How I wrote this means, K, you write a K into K matrix, that is 3 into 3 matrix. Okay, that is K1 1 K2 1 K1 3. Okay, and second row 2 1 2 2 2 3 3 1 3 2 3 3. The third element that I wrote here K1 3 K2 3 and K3 3, and which is multiplied with this distance, that is 0.12. Okay, so which is equal to this is 0.12, nothing but maximum displacement. We are going to consider the A3 value. So A3 is equal to 0.12. So to switch. Okay, so the equilibrium condition, what is the formula? Kq is equal to F. So substitute global stiffness matrix, Q value and the force value which is there in this. Okay, then again you simplify this, apply the boundary condition here. So node here the node 1 and node 3 are fixed, so delete first row first column, and one more third row is there, third row third column, remaining is this second element, this one is the remaining element. So 8 into 10 to the power of 5 Q2, this is F2 minus K2 A3. So A3 also we know, substitute all the values, you are going to get Q2 is equal to 0.81. Okay, so this is the displacement. Okay, therefore the nodal displacement vector is equal to what? Q is equal to 0, this is the Q1, and Q2 already calculate 0.81, and this is the 0.12 they given. Okay, transpose of that. Okay, like this you have to calculate the boundary conditions in the the distance gap problem. Here in the distance gap problem you have to consider like this. Okay, this is the only trick, remaining procedure is same only. Okay, so next, go for stress in each element. Stress is equal to E by LE 1 minus 1 1 U1 U2 or Q1 Q2. For first element 1, you know the Young modulus, we know the length. Substitute, you are going to get the stress for first element is equal to 1080 megapascal or Newton per mm square. Okay, similarly second element, again E2, just to replace here E2 L2, substitute the E2 L2 value. So here 2 3 is here 192, here 2 and 3 node number. Okay, substitute, you are going to get the minus 920 megapascal or kilo, that is what? Newton per mm square. Stress in each element. Already we know the support reaction formula for the elimination method. This is the formula, R is equal to KQ minus F. So R1 R2 R3. So substitute in the values. Okay, so just to multiply this, you are going to get, so first row first column you have to multiply, you are going to get this minus of as it is. Okay, then again you subtract this, you are going to get this equation. So this is the support reaction at the given node, R1 R2 R3. At R1 is equal to minus 324 into 10 to the power of 3 acting opposite. Here there is R2, there will be no reaction, and R3 is also acting opposite direction. Okay, like that you have to solve the numerical problems on belongs to the distance gap problem. In the distance gap problem only this is the trick. Okay, remaining procedure is same. Okay, this is most important to consider force value in the equilibrium condition. Okay, so this is about what the problem 3, that is problems on this what distance gap problem. Okay, like that you have to solve the numerical problems on what distance gap problem. So here main thing is in the distance gap problem here the force you have to consider very important here. Okay, in while substituting the equilibrium condition. Okay, so I hope you understand this problem. Okay, thank you.